Okay, in this presentation we're going to look at a counting problem. So what we're going to look at here is this question here. So you must create a password of length 5 using the following characters, okay? And so the characters are A, B, C, D, 1, 2, 3, 4. So let's just highlight the key pieces of information there. Length 5, okay? And the fact that we have these 8 characters. There's 8 there, 4 of which are letters and 4 of which are numbers. Okay, bear that in mind. So how many possible passwords are there? So the approach I'm going to use, and this question is almost too simplistic to use this approach, but it's a good idea to actually get used to the approach first, is actually sort of set out each of the 5 positions. So this is the first position, second position, third position, fourth position, fifth position, and so on, and talk about how many options there are for each of those positions. Okay, so in the first instance, essentially there are no constraints in this example. Okay, we get to assume that we can repeat a character that we've used already. For example, we can have 11A 3, 4, something like that. So we have no constraints. We can use any of the 8 here, any of the 8 here, 8, 8, and 8. Okay, so it's 8 to the power of 5, which is 32,768 using my calculator. Okay, so that's so far so good. Now, what if you only use letters? That means we can't use numbers. That's an important thing to remember. No numbers, okay? Just actually remember that. No numbers whatsoever, okay? Now, I'm just sort of flagging that because it sort of comes in helpful for a question that we have later on. And usually that's actually sort of what happens, actually, that, it's a sort of a thing you will see in mathematical questions, that a previous question usually contains some sort of trick for a question that comes later on. Anyway, so we have 4 letters, A, B, C, D. Okay, that's all. So we have 4 options for each each position. 4 times 4 times 4 times 4 times 4. Okay, so that is 4 to the power of 5, and that is 1,024. Okay. So, sorry, I went through it very briskly there, so I just put that back. Now, so let's go on to the next question there, with a bit more decorum. What if the first character cannot be a number? So now you can sort of see where my approach will come in useful. Okay? So, 1, 2, 3, 4, 5. Okay. So there's a constraint on the first position. It cannot be a number. That means it can only be a letter, and we have 4 letters that we can choose from. Okay, so we have 4 options there, and 8 for every other position. Okay, so 4 times 8 to the power of 4, that is 16,384. Okay, that's good. And yeah, okay, so I'll just move on from that. Now, how many passwords contain at least one number? Always watch out for questions with at least. That means it could have one number, it could have 2 numbers, it could have 3 numbers, it could have 4 numbers, or it could have 5 numbers. There's so many to choose from. There's so many possibilities there. The only possibility that is not allowed is no numbers. So the complement of this is no numbers. Okay, so essentially what we're going to do here is use part A and part B to help us here. So A is the all possible passwords. Okay, constructively, that is the universal set. Okay, if you remember set theory. Okay, so B is the no numbers set. Okay, so the number of the number of possible passwords where there's at least one number is the complement of the set of passwords with no numbers. Okay, so it's essentially the difference between the two. Okay, so essentially that just actually requires a little bit of lateral thinking like that. So it is, this is the answer from part A, 32,768, minus the number of passwords with no numbers, okay, and that is 1,024, and this would give us 31,744. Okay, so that is the answer to that one. Okay, so it's, yeah, so that is a very quick way of doing it. But if you were trying to do it any other way, you could get it out, but it would take forever. Okay, so this is just the sort of thing in, like, particularly when you get into probability, is when I sort of see something like this, at least one. This is the sort of, if you were to do it exactly as you would, the direct approach, it would take a long time. So this is where the complements sets or complement probabilities comes in very useful. Okay, it's something you sort of, this is a skill you build up. Now I better keep going and go into the last question here. What if each character must be different? Okay, so we never seen this constraint before. Okay, so this means if a character has been used already, it means it can't be used again. So for example, we have, let's just say we're assigning our characters from left to right, okay? And just to start off with, we have 8 possible options there. There's no constraints yet. We haven't used one of the characters yet, but so we have all 8 available to us. But now we've used one, so we're going on to position 2, and we've only got 7 left, okay? Whatever was put in position 1 is gone, okay? So in this case, we have 7 options to choose from, okay? And now we move on. So we've used 2, we've only got 6 left here. And now we've used 3, we've only got 5 left. And now we only have 4 left for position 5. So 8 by 7 by 6 by 5 by 4, that is 6,720. Okay, so that is this presentation done. I'll leave it there.